Example 9.6 CD player. In example 9.2, we established that a CD track is 5.4 kilometer long. A music CD can store 74 minutes of music. What are the angular velocity and the tangential acceleration of the disc as it spins inside the CD player, assuming a constant linear velocity? So here they have given you the total length of the disk, which I can write as L equals 5.4 kilometer. Kilometer you can convert to meter by multiplying this term with 1000 or 10 to the power 3 meter. Then this music player can store music of 74 minutes. So my time interval delta t is 74 minutes, which I can convert to second by multiplying it with 60, since every minute has 60 seconds. And when you do that, you get the time in seconds as 4,440 seconds. We need to find what are the angular velocity and tangential acceleration. So I want to find omega and alpha as the disk spins inside a CD player. Before we find these values, we can first find what is the constant linear velocity v. I have the total length of the CD player and I have the time for which it can play music. Using these two values, we can calculate the linear velocity v as length over delta t, which is equal to 5.4 times 10 to the power 3 divided by the time 4,440 seconds. And when you solve this, you get the linear speed of the disk to be equal to 1.216 meter per second. Now the CD is a spiral, starting with an inner radius R1 of 25 millimeter and reaching an outer radius R2 of 58 millimeter. These values of R1 and R2 were given in example problem 9.2, and I have taken these values from that problem. We can approximate the spiral track at a particular radius to be almost circular so that we can use the relationship between linear speed and angular speed. So if I want to find the angular velocity omega, I'm going to use the relationship between them. We know that v is equal to r times omega. So I can calculate omega by dividing v with r. And I will find this omega values both at the inner radius and the outer radius. So we write omega 1, which will be the angular speed at the inner radius. We will take this as v, the linear speed over r1. R1 is 25 millimeter, which you can write as 25 times 10 to the power negative 3 meter. Same with R2, this millimeter I will convert to meter by multiplying the number with 10 to the power negative 3. Now substitute. Linear speed is 1.216 divided by the radius, which is 25 times 10 to the power negative 3. And when you solve this, you get omega 1 to be equal to 48.64 radian per second. Then I do the same thing for radius R2, the outer radius. I find the angular speed at that point. We write that as omega 2, which will be equal to V over R2. V remains the same since it is constant, 1.216. Outer radius is 58 millimeters, so 58 times 10 to the power negative 3. And that gives me angular speed at the outer radius to be equal to 26.97 radian per second. Looking at the value of omega 1 and omega 2, we notice that the CD has to slow the disk rate of rotation during the course of playing it. So after we find the angular speed, we can find the angular acceleration alpha. We know that alpha is equal to change in angular velocity over the change in time. Change in angular velocity will be nothing but the final velocity, which is omega 2 here, minus the initial velocity omega 1 over the change in time. Now substitute. Final is 26.97. Initial is 48.64. Divide by the time value, which is 4440 seconds. And when you solve this, you get your angular acceleration alpha to be equal to negative 6.23 times 10 to the power negative t radian per second squared. Example 9.7, hammer throw. One of the most interesting events in a track and field competition is the hammer throw. The task is to throw the hammer, a 12 centimeter diameter iron ball attached to a grip by a steel cable, a maximum distance. The hammer's total length is 121.5 centimeter and its total mass is 7.26 kilogram. The athlete has to accomplish the throw from within the circle of radius 2.13 meter, which is equivalent to 7 feet. And the best way to throw the hammer is for the athlete to spin, allowing the hammer to move in a circle around him before releasing it. So here they have given you an example of an Olympic game where a thrower took 7 turns before releasing the hammer. And the period to complete each turn was obtained from examining the video recording frame by frame. So this is the time period for each turn, and he took 7 turns before releasing the hammer. Problem 1 is asking you, what is the average angular acceleration during the 7 turns? So I have the time period for each turn. Using that, I can find the total time for the 7 turns. And we can also calculate the value of angle theta because we know we are taking 7 turns. And using that information, I can find what is theta. And then later I can find the average angular acceleration alpha by using the equation of motion. So let us start with finding the time t first. Here I have the time for each turn. And I can find the total time t for all the turns by adding each time value. So let us add them. The all will be 1.52 plus 1.08 plus 0.72 plus 0.56 plus 0.44 plus 0.40 plus 0.36. And when you add all the time values, you get the total time to be equal to 5.08 seconds. After I have the total time, I need to find what is the total angle theta. We know that theta for 1 turn is equivalent to 2 pi. So if I want to find theta for 7 turns, I will just multiply this 2 pi with 7. That will give me 14 pi radian. This is my theta. After finding these two values, now I can calculate the average angular acceleration. To find the angular acceleration alpha, I'm going to use the first equation of motion, which says theta final is equal to theta initial plus omega initial t plus half alpha t squared. So we move this theta initial to the other side, we get theta final minus theta initial to be equal to omega initial is the initial angular velocity, and since we started from rest, initial angular velocity at rest will be 0. So this whole term becomes 0 plus half alpha t squared. Theta final minus theta initial is my delta theta, which will be equal to half alpha t squared. I have delta theta, which is the total angle over here, which is 14 pi radian. I have the time t. You can use shift solve to calculate the angular acceleration alpha, or you can rearrange the term to write alpha as 2 delta theta over t squared. Now substitute 2 times 14 pi divided by t squared, which is 5.08 squared. And when you solve this, you get the angular acceleration alpha to be equal to 3.41 radian per second squared. This is my alpha. Problem 2 is asking us, assuming that the radius of the circle on which the hammer moves is 1.67 meter, the length of the hammer plus the arms of the athlete, what is the linear speed with which the hammer is released? Now, if I want to find the linear speed with which the hammer is released, I need to first find what is the angular speed omega with which it was released. Because I don't have the linear displacement, so I cannot use linear displacement and time to find the linear speed. But I have the angular displacement, I have the angular acceleration. I can use these values to find angular speed omega. And using the relationship between linear speed and omega, I will find the linear speed. We have the angular acceleration alpha, and we can write alpha as change in angular velocity over the time interval delta t. We can solve for alpha. Change in angular velocity is nothing but the final angular velocity minus the initial angular velocity over the change in time. Since initial angular velocity is 0, we can just write alpha as omega final over the time t. So we can calculate omega final by multiplying alpha with the time interval delta t. I have both the values, just multiply them. Alpha is 3.41 times time t is 5.08 seconds. And when you solve this, you get the final angular speed to be equal to 17.3 radian per second. After I find the final angular speed, I can calculate the linear speed. The relationship between them is linear speed is r times angular speed. The radius of the circular path is given to us, which is r equals 1.67 meter. Just substitute here, you get linear speed v as r is 1.67 times 17.3 radian per second. That gives me linear speed v as 28.9 meter per second. So this completes part 2. In problem 3, they're asking you what is the centripetal force that the hammer thrower has to exert on the hammer right before he releases it. So we need to find the centripetal force Fc. We know centripetal force is given as mass times centripetal acceleration. And since I have the angular speed omega and I have the radius of the circular path, I'm going to choose centripetal acceleration to be equal to r omega squared to substitute here in calculating the force. So I will write centripetal acceleration AC as r times omega squared. Now we can substitute all our values to calculate the centripetal force. The mass of the hammer is 7.26 kilogram, which was mentioned in the question before. I'm going to substitute that here. So we get centripetal force Fc as 7.26 times the radius, which is 1.67 times the angular velocity, which is 17.3 squared. And when you solve this, you get the centripetal force as 3,630 Newton. Problem 4. After release, what is the direction in which the hammer moves? Now we have discussed in circular motion. If you have an object which is going along the circular path, the linear speed of the object is always tangential to the circular path. So if I were to release that object at any point in the circular path, that object continues to go along the linear velocity, that is along the tangent to that point. So if I were to release my object at this point here, it will follow the tangent to the point when it is released. The same thing over here with the hammer. If the hammer is released at any of the point here, the hammer will follow the tangential path after release. So let's say if it is released at this point here, indicated by the white arrow, the hammer will follow the path of the linear velocity at that point. That is, it will move along the tangent to that point, along this tangent shown over here. So whenever an object is released in circular motion, it moves along the tangent to the point. Tangent to the point in the direction of linear speed v.